a quantity what sell. Carry me ackee, gonna lynch the market, and not a quantity what sell.
I'm David Van Vranken, and I want to welcome everybody to our 14th lecture in the Chemistry 51C series during the fall quarter of 2020 here at UC Irvine. I'm not sure how many of you knew that the national dish of Jamaica is ackee and saltfish. And when I first ran into this on a YouTube video, I had no idea what ackee was. It turns out that ackee is a fruit. And I was wondering, how come I've never seen ackee fruit in any store or at any farmer's market or in any place in my life? How can it be so unusual? How can it be so popular in Jamaica and yet so unusual to find in the United States? And here's what I found out that seems rather interesting.
So this is what the ackee should look like when you purchase it. If it's not open up like that, it is poisonous if you try to force. If it's closed like this, close up and show them. So if the ackee is closed up like that, then it's poisonous. When you purchase them at the farmer's market, they should be open like that, freely. You know, so they pick them off the tree and they're open up like that. And show them how you deal with it now, mommy.
Open it. And this is one. All three is one ackee.
So one pod give you 3 ackee. You know what I say? So you open them up. You can just use your hand for this one. And then of course that black thing you're looking at, this is the seed. And you can replant those. You feel what I say?
It turns out that ackee fruit are toxic. In the normal form of the fruit that you have growing on the tree, they're closed up in these embodied fruits. But then as they get older and they mature, they split open on their own. And once they split open, then they are safe for you to eat. And that's interesting to me. How can it be that there's something that's present in there, and then as it matures, the toxicity goes away? And let's go and try to understand more about what's going on with the insides of these ackee fruit. What you're eating with ackee fruit are these components of the fruit called the aryls. It contains a seed, and then it contains this fleshy portion that you can boil and then serve with salted cod codfish that's been dried out and salted. You soak the salt out. It turns out that the immature fruits, this immature fleshy part, the aryl of the ackee fruit, contains a compound called hypoglycin A. And as the fruit matures, the concentrations of hypoglycin A drop by about 10,000-fold, down to levels that are safe for you to eat. And what happens is that hypoglycin A, it looks kind of like an amino acid. So if you've taken a class already where you learn the structures of the amino acids, this slightly resembles, because there's this greasy part sticking off of here, it slightly resembles leucine, isoleucine. It has one more carbon than those. Obviously, the methylene cyclopropane is nothing like any normal ribosomally encoded amino acid in the human body or in any normal living organism. But this fruit produces this hypoglycin A, which is not in itself toxic, but your body converts it into something toxic, which is such a common feature of many toxic compounds. So normally when foreign-looking molecules get into the human body, they end up getting converted by the liver quite often, or sometimes within the cell, but within the target cell. But oftentimes in the liver, that's your garbage disposal of the molecular garbage disposal of the human body. What happens with hypoglycin A is that all cells contain aminotransferases that convert back and forth amino acids into alpha keto carboxylic acids. This is a keto group. It's at the alpha position of a carboxylic acid. And that's in equilibrium. And then it turns out that there's an enzyme called oxoglutarate dehydrogenase. And I can't remember if that's part of the Krebs cycle or one of these cycles that you memorize in your biochemistry class, which would be probably Bio 98 here at UC Irvine. But you lose this carboxyl group. This is all enzymatically promoted, and it converts it into a thiol ester instead of an oxygen-based ester. And that's really the part that is toxic. Once it gets converted into this metabolite that's not natural, this thiol ester, this CoA ester, that then reacts with a part of the enzyme or a cofactor in the enzyme to form a covalent bond. And then when that radical part adds to this carbon atom here at the end, that thing ends up covalently stuck to the enzyme. It deactivates the enzyme, and it leads to this syndrome called Jamaican vomiting sickness. And so maybe that's why they don't sell that fruit here in the United States. They sell cans of it. I'm sure I could get on the web and buy cans because they don't can it until the fruit are ripe. But maybe that's why they don't sell the fruit here in the United States. Maybe people are too worried that somebody will accidentally sell unripe ackee fruit and somebody will get sick. So hypoglycin A. You know, naturally occurring toxins are often the origins of many drugs. You know, molecules that have specifically target enzymes in human body often can be used to treat diseases associated with those enzymes. So always be curious about why any molecules from nature might be toxic, because there's usually something interesting in there. All right, we're in the chapter on carboxylic acid derivatives. Chapter 22 in the Gorzynski-Smith textbook. That's the 5th edition. And we've been talking about reactions of acid chlorides. I showed you that you could take acid chlorides and with extreme efficiency convert acid chlorides into esters and amides. And I gave you a mechanism when we left off for reaction of amines, and it's the same reaction mechanism if you have an ester. You just use an oxygen lone pair instead of a nitrogen lone pair. And forming amides, you add to the carbonyl, you deprotonate the atom that just added, like I'm shown over here, and then you kick out the leaving group chloride in the next step. So let's keep going with talking about transformations, functional group transformations of carboxylic acid derivatives. Okay, we have to talk about acid chlorides. Man, they are so reactive. And the book teaches you some reactions of acid chlorides just to prove how reactive they are. But honestly, these two reactions I'm going to show you that are in the book are pointless. You would never use these on purpose. In fact, this would be, the top one here is really a side reaction. So anytime, if you were trying to add, I'll just give this as an example. If you were trying to make an ester using this acid chloride, maybe an isopropyl ester, and you would add pyridine as a base to soak up the HCl that's generated, you have to worry about keeping your reactions absolutely free of water. Because if you get any water in there, then you're going to be stuck worrying about this issue of water attacking fast. It'll attack slightly faster than the isopropanol or any other alcohol you put in there. It's less hindered, just seems more mobile. So under typical conditions, the typical reaction conditions for these kinds of reactions where you're trying to make an ester, if you got water in there, you'd end up with either the main product or an additional side product that you do not want. You'd end up with the carboxylic acid. And I promise you, you do not want to transform an acyl chloride into a carboxylic acid, because invariably you just made that acyl chloride from a carboxylic acid. So why would you want to convert it back? Nobody would ever want to do that. So usually this is a side reaction. Let me just write that down here so we're clear about why is this an important thing to worry about. This whole thing here is an unwanted side reaction. Side, I'm not doing a good job spelling side reaction. Unwanted side reaction. So avoid that. Keep water out of your reactions. In the lab, we go through so much work to keep our reactions under nitrogen gas that is free of moisture, free of water, free of molecular oxygen. We keep water out of our reactions because we like to use reagents like butylithium or Grignard reagents or acyl chlorides that are so reactive that they instantly react with water. So avoid that side reaction. Keep water out of your reactions. We don't stir things open to the air in our laboratories. There's another transformation that they show you in the book for acid chlorides. Acid chlorides are just so reactive. If you take a carboxylate anion, and let me draw another common representation, which I'm not a big fan of, but but it might help you to better think about what's going on here. This is how you'll often see depicted sodium carboxylate anions. So the sodium salts of carboxylic acids or the potassium salts, they're often shown as free anions. And if you expose an acyl chloride to a carboxylate anion, doesn't matter whether it's a sodium salt or a potassium salt, the O- on there will attack, and you'll end up generating an anhydride. In this case, sodium chloride would be the byproduct. And so they tell you about this in section 22.9 of the book. I'll just put chapter 22.9. But why would you do that? Why would you use an acid chloride to make an anhydride? The only thing that we do with anhydrides in our course is we use them to make esters and amides. So let's just use this as an example. Suppose we wanted to use acetic anhydride to make an amide with aniline, and we have to add an amine. If we're doing amines, we have to use we can't use pyridine as a base. We have to use triethylamine as a base. And this would be good conditions for using the acetic anhydride, for using that carboxylic acid anhydride as an acylating agent in order to form an amide. But if you were just trying to form that amide, you could have done that starting from the acid chloride. You didn't say, you actually added an extra step by synthesizing the anhydride. We could have used exactly these same conditions, which is aniline and triethylamine. We could have used exactly those same conditions to form the amide from the acid chloride. So it doesn't seem like it's really a useful reaction to synthesize an anhydride from an acid chloride at this stage of your career in a sophomore organic chemistry course. So that seems, you can certainly make anhydrides if you want, but no chemist really does that I know of, or it would be super rare. And here's why: because anhydrides are typically these reagents. They're about 100,000 times less reactive than acid chlorides. That means they're more stable to store on the shelf in a bottle. There's less worry that a little wet air is going to get in there, and they're going to decompose more slowly. So the reason to use anhydrides is because they're easier to store and less reactive. That's not a concern for you when you're taking an exam. You don't care how easy it is to store a reagent. So typically anhydrides, we buy them and we just store them on the shelf. We don't make them in the lab. So I'll show you 3 of the common ones that every lab has sitting on their shelf, every synthetic organic chemistry lab. One of them is acetic anhydride. And so it's formed from acetic acid. So 2 molecules of acetic acid can be condensed to form acetic anhydride. Here's the chemical structure of acetic anhydride. And we buy this. We have huge bottles of acetic anhydride in the lab because it's so inexpensive and easy to store. Now, what you'll find is that we typically abbreviate this functional group. I think I've mentioned this before. I'll try to indicate this. This functional group right here is called an acetyl group, acetyl. And the abbreviation for acetyl is AC, capital A, small c. That's the standard abbreviation for an acetyl group in the field of organic chemistry. And so since there's 2 of these acetyls on one oxygen, we often abbreviate this reagent as AC2O. There's 2 acetyls on that oxygen. I've put a box around one of them. But acetic anhydride is so common. If you want to make an acetyl amide or an acetyl ester, an acetyl thioester like acetyl-CoA, if you wanted to, you'd use acetic anhydride as an inexpensive reagent for doing that. Okay, another anhydride that I'm pretty sure you've seen before in our organic chemistry series in the Gorzynski-Smith textbook is maleic anhydride. And it turns out that this double bond here, the place you've seen this is not using the anhydride functional group. It's using this alkene here. This is great for Diels-Alder reactions. It's great as a dienophile for reacting with dienes. So I'll just remind you that you might have seen this because it is so commonly used for, I better spell this out. I was going to write DA. Great for Diels-Alder reactions. So 4+2 cycloadditions. Reactions it's really good for making that 2-carbon double bond is good for 4+2 cycloaddition reactions. That's where it's commonly used. Okay, another pretty common anhydride that I think pretty much every lab here is organic chemistry lab here at UC Irvine has sitting around is phthalic anhydride. We don't pronounce the the f sound, the pH sound. Just everybody says phthalic anhydride. And so let's go ahead and draw out the structure of phthalic anhydride. It's just like maleic anhydride, except there's a benzene ring fused on there. And so let me go ahead and draw. There's the structure of phthalic anhydride. So it's a benzene ring fused on, and you can use that to make amides. Now, you'll have to be a little bit careful about this. We've put some problems on next week's problem set to help you practice. Once you add to one side of an anhydride, the other side pops off. And so it's important for you to practice using cyclic substrates. Like, what happens if you add a nucleophile? We're going to ask you to think about this in discussion section. What happens if you add a nucleophile in with one of these cyclic anhydrides? Eventually in the next step, we're going to pop off that to the other side, but it'll still be attached. It's attached to the molecule. Okay, so what do you use anhydrides for? You use them the same way you use acid chlorides. So here's an example. If you wanted to take this alcohol and convert it into an acetyl ester, you could use acetic anhydride, like I've shown here at the bottom. For alcohols, like the one that I'm showing here, we use pyridine as a base. If that was an amino group, we'd use triethylamine as the base. And so this would generate, let's go ahead and draw out the organic products here, but this will generate an acetyl ester because we're using acetic anhydride. Right? We're not messing around right now with this stereogenic center. We don't break or form any bonds there. And so if we started with wedge up as our stereochemistry, that means it's still going to be with the stereochemistry up. And so now we'll have an ester bond there. You could have done this same reaction with acetyl chloride. I think the part that's a little more challenging is usually we tell you, show all the organic products. And there's an organic byproduct that nobody cares about in this reaction when you use an anhydride. And that organic byproduct is the other end of the acetate. So maybe let me go ahead and draw the other end of the acetate here. So acetic anhydride has two carbonyl groups. Here's the other one. It's this acetate anion leaving group. And so how do we balance this out? We can't have an overall negative charge that's not balanced out by something. It turns out that the pyridine, because you generate acetic acid as the overall byproduct for the reaction, you end up with this pyridinium ion. I hope I can fit that circle around there. So that's supposed to be pyridinium. So you can kind of see where these pieces come from. I wonder if I can highlight this. See that H right there? That H ends up on the pyridinium. It doesn't get deprotonated in the first step, but it ends up eventually after a multi-step mechanism on that pyridinium. And then this other part over here, let me see if I can pick a different color here to highlight stuff. This other acetyl group ends up, whoops, let me get the oxygen too. There we go, ends up right there. And the acetyl ends up attached to our substrate, just so you can see the little pieces there. All right, so anhydrides, again, in the lab, we like things that are inexpensive and easy to store. That's the advantage of anhydrides. When you're a student in an organic chemistry class, honestly, do you care whether it's easy to store on the shelf or inexpensive? Not really. So it's kind of hard to explain why that's a useful property. Okay, anhydrides are way more reactive than esters. They're not as reactive as acid chlorides, but they are way more reactive than esters. And so why is it that the oxygen that you have here on the anhydride doesn't deactivate the carbonyl as much as an ester? So I think one of the things we pointed out to you is that it's the lone pairs here that really have this deactivating effect on neighboring carbonyl groups. And so why are the carbonyls of acetic anhydride so reactive? Well, the reason is because there's two carbonyl groups, and that lone pair is donating into both carbonyls at the same time. So you can think of it like you're only getting 50% donation into the carbonyl. You're only getting 50% deactivation of the carbonyl with an anhydride. So there's this problem that the lone pair, if you want to describe it as a problem, donates into two different carbonyls at the same time. So you're only getting half of that deactivation effect. You might be wondering why. It's like, whoa, isn't there another lone pair? You can't have two lone pairs aligned at the same time. They're in orthogonal orbitals. They can't, both the lone pairs on that center oxygen cannot simultaneously donate into different carbonyl groups. There's only one lone pair that will have the correct geometry to be aligned with the pi systems of the carbonyls. Okay, so that only one lone pair can donate into the carbonyl, and now it's donating into two carbonyls, so you're getting kind of half the deactivation effect. And if the carbonyl is not deactivated, that means it's reactive. Let's go ahead and take a look at the mechanism. It's just like the mechanism for an acid chloride, but I'll draw it out anyways because it's good practice. So just like the mechanism for an acid chloride. So here I'm going to use the alcohol. We would typically have, since it's an alcohol, you'd typically run these reactions with pyridine in there. Let's go and draw out that mechanism. I'm going to take the lone pair on the alcohol, but if you had an amine, it would be the amine lone pair that would be attacking. And I'll push I could attack either carbonyl. I'm just choosing to do the one here on the left-hand side. There's the two carbonyls on the anhydride are indistinguishable. And so now I'm going to generate this intermediate. Well, let me do it in very high contrast black color here. I'm going to draw out this intermediate where I have the nucleophilic oxygen that just attacked. It's got now that I got 3 bonds on there, I need to have a positive charge. We call it an oxonium ion when there's 3 bonds to oxygen. So I've got this protonated oxygen, this oxonium ion. My carbonyl now is in alkoxide O- group. And I still have this other acetate group just sitting there waiting to act as a leaving group. But just like the acid chloride, we have to deprotonate our nucleophile, the oxonium ion, before we push out the leaving group. So I'm going to go ahead and draw my basic species using a symbolic B. That would be the pyridine in our reaction. And so then we'll draw a deprotonation of this oxonium ion that'll set us up to really, in a speedy manner, push out the leaving group. So here we go. And now we're ready to push out this acetate leaving group. This is so easy. You know, this is a fast step for the reaction. Chloride, acetate, all kinds of things will be pushed out very quickly. The slow step of the reaction is getting the initial alcohol to attack. Everything after that is fast. So you might think that, well, I've never seen acetate act as a leaving group. Look, there's a lone pair right here. Let me darken. My gosh, that's nucleophilic. It has no problem whatsoever pushing out a chloride or an acetate, a hydroxide, an alkoxide. No problem. This is not the slow step. So even if that acetate looks unfamiliar to you as a leaving group, that's still fast. That is fast. Okay, let's go ahead and draw out the next intermediate. It's going to have this, now we've got our ester here, OR, and we've got that acetate leaving group, and we've got the protonated base, HB. I'm not going to draw that out here, but you can see that acetate acted as a leaving group. Okay, so just like the acid chloride. Okay, what about carboxylic acids? If you can attack esters, you can attack anhydrides, you can attack what about carboxylic acids? Well, we're going to run into a problem here. And the problem is that this proton, my gosh, what a problem that thing creates. That proton right there causes a wealth of problems because any reagent you use that is nucleophilic enough to add to the carbonyl over here like this is also going to react with the proton. It's going to pull the proton off faster than it adds to the carbonyl, always. There's no way to win in this competition. If you put in a carboxylic acid, you may think, oh, well, didn't Van Vranken say that you always attack carbonyls? Yeah, but when there's an acidic proton, this is a carboxylic acid, the fastest thing to happen is the acid-base reaction. You know, protons are in the first row of the periodic table. They vibrate quickly. You pull them off quickly. Carbon atoms in carbonyl groups are in the second row of the periodic table. You attack those more slowly. So, you know, we've run into this situation here where it's always going to be faster to deprotonate. And once we deprotonate, you're going to end up stuck with this thing that's even less reactive. Let me draw up what you would get after this acid-base reaction is over. I guess I don't need to draw all the lone pairs. I'm just going to draw one of them. There we go. That's what you would get. And if you were using a thiazide anion, now you've kind of ruined your great nucleophile. We used to have this great nucleophile in here, the ethoxide. Now all we have is an alcohol, which is not a great nucleophile. And now our electrophilic carbonyl group is even less electrophilic. This is now unreactive because there's an O- next door. And I gave you, a set of reactivities, and carboxylate anion carbonyls are among the least reactive carbonyls you can imagine. So because of this fast acid-base reaction, we're going to have a challenge trying to get nucleophiles to attack carboxylic acids that have OHs on them. And so you're just not going to see, I'll draw it here, but you're just not going to see, it's going to turn out to be very challenging to add in to carboxylic acids using strong nucleophiles. Because anything you do to make the nucleophile even stronger, it's also going to be more basic. It's simply going to deprotonate faster. You can't win. Oh yeah, I'll make the nucleophile 1 billion times stronger. Well, it's going to be 1 billion times faster at deprotonating. So how do we fix this problem? How do we get things to add to carboxylic acids? Our trick that we're going to use is we're going to protonate the carbonyl. We're going to use acidic conditions. And so if we have an H on here and we want to get an alcohol to attack, alcohols are lame nucleophiles. If we wanted to get this attack, instead of making our nucleophile more nucleophilic, we're going to make the carbonyl group more electrophilic by protonating it. Just like we did in the previous chapter for making ketals and acetals. And if you protonate the carbonyl, even a lame nucleophile like an alcohol can attack that. So that's what we do with the conditions in order to make this work. So now, no problem adding to that. It's not easy to stick a proton on a carbonyl group, but if you can do that, then we can get oxygen nucleophiles to attack. Okay, so what kinds of reagents we'll get back to that later. Okay, so we're going to come back to that later. But let's talk about making acid chlorides. And we use a reagent that we've seen before. It's a reagent that you saw way back in an earlier chapter of the book, back in section 9.12, which was on alcohols and converting them into alkyl halide leaving groups. And we showed you a set of conditions that uses thionyl chloride. And I don't know if I have that word here. This is called thionyl chloride, SOCl2 is thionyl chloride. And you've seen the use of this thionyl chloride where you use thionyl chloride and pyridine as a base to soak up the HCl. You can convert alcohols into alkyl chlorides and then do SN2 reactions on them. I expect you to still know that. Or you could, another way to put a leaving group in there is to make a tosylate out of that OH group. Okay, we're going to use very similar conditions for making the acyl chloride. I already showed you this at the beginning, but we don't use pyridine for this. So that's really the thing you're going to have a tendency, if you've got a great memory for what we did earlier with alcohols, you might think we're going to use pyridine, but that's not the trick here. It's like we're going to use heat here, and you get HCl as a byproduct, but you don't soak that up. You let the conditions stay acidic. And typically we have a condenser on our reaction as we boil it in benzene usually, and you just put this little tube on there and hydrochloric acid gas, HCl gas, just escapes and then smokes out of your reaction. So over here with the alcohols, we wanted to prevent the conditions from becoming super acidic. But here with acid chlorides, for making acyl chlorides, we just let the HCl bubble out of the reaction. So heat, don't use pyridine, it wouldn't work. If you put the pyridine in here, you wouldn't get the reaction to work. Okay, and man, you're going to need this reaction. You're going to need to make acyl chlorides. I'm sure we're asking you to do this somewhere on the practice problem set, on sapling, in discussion sections. I can't imagine an exam in any organic chemistry class where they didn't get you to do this, because acid chlorides are good for making every carboxylic acid derivative. They're the most reactive carboxylic acid derivative, and you can use them to make anything. So, man, just total, I don't know how to, I'm just going to say it again, it's total money. It's a money reaction that you're going to end up using all the time if you're taking any course in organic chemistry that involves synthesis. Money. Oh, man, that is money. All right. Okay, let's come back to this this challenge of adding to carboxylic acids. We've got this super annoying proton on here where anything we do to put in strong nucleophiles, they'll also be strong bases. So our trick here is not to put in powerful nucleophiles. What we do is we convert the ester into a powerful electrophile. So we add acids to these reactions. In theory, you could add toluene sulfonic acid, but toluene sulfonic acid is it's a little bit expensive. You don't want to dump in a ton of it, and you need high concentrations of acid to get faster rates for these types of esterifications. So whenever you take an alcohol and you take a carboxylic acid, so here's an alcohol and here's a carboxylic acid, and you add an acid catalyst, you will catalyze equilibration back and forth. Back and forth, you'll catalyze equilibration to make the ester. And then if you start with a carboxylic acid, you end up with water as a leaving group. It's merely an equilibration. You're just accelerating the rate at which you equilibrate to reach equilibrium. And the way we make this useful is you drive the equilibrium to one side or the other. So if you use excess methanol, you'll end up with a high yield of the ester. It'll drive the equilibrium toward the ester. If you use the same conditions, take an ester in water and add hydrochloric acid, if you have excess water, you'll drive it back to hydrolysis to the carboxylic acid. So when we run this reaction in the direction, in the direction where we're favoring the ester, we refer to that as a Fischer esterification. It's a useful procedure, and all you need is an alcohol in this super cheap reagent, typically hydrochloric acid or sulfuric acid. Again, those are more common than toluene sulfonic acid, but you could put PTSOH if you wanted, but I'd be like, what? I've never seen that before. But in theory, that's correct. But I would prefer you just write HCl. And because it's easier to write than H2SO4, and it's easier to write than TSOH. And it's a very common set of conditions for performing this Fischer esterification. That's Emil Fischer. They were doing this back in the 1800s. Wow. Yeah, I think they were still riding in horses and buggies back at that time when this reaction was developed. Okay, you need an excess of the alcohol to make this work. In order to drive the equilibrium, to make this useful, right? If you want high yields, if you want a high yield of this ester over here, then you need an excess of the alcohol. Excess, hope I'm spelling that correctly. So an excess of the alcohol will lead to a high yield. So if you have to use the alcohol in excess, it better be cheap. And so you only see this used with cheap alcohols. And there's really only two common choices here. One common choice is methanol or ethanol. And in theory, you could do isopropanol. I've never seen that done in 25 years, people making isopropyl esters. Because usually this is just a throwaway part of the molecule. We're going to treat the ester with dibal H or something and just cleave that part off, or lithium aluminum hydride or a Grignard reagent. And we throw that part away. So we just want something small. And methyl and ethyl are the common groups that we put on there because we can make them with methanol and ethanol, which pretty cheap. You need super strong acids. As I mentioned before, hydrochloric acid is the easiest one for you to write, but you could also use sulfuric acid. Again, in theory, you could use toluene sulfonic acid. Nobody does that. Okay, I would prefer that you showed heat. I don't always demand that. Let me go ahead and write this out with HCl here. Let's go ahead and draw out a version of this reaction. So if you wanted to draw out this Fischer esterification to convert this carboxylic acid into an ethyl ester, how would we do that? Well, one simple way is just to write the reagent HCl here. But how do we indicate that ethanol is present in excess? We could write ethanol as a reagent over here and then write the word excess. But more commonly, if the alcohol is a common solvent, that means all we have to do is write it below the arrow, and everybody will understand that means it's in excess. You don't even need to write the word excess. You could, but the solvent is always present in excess. So below the arrow, if it's a liquid material, if you put it below the arrow, that means you're using it as a solvent for the reaction. And you don't need to write the word excess. Now, I prefer that you write the word heat here. If you're asked for the reagents, but I think in some of the sapling problem sets, we don't require the word heat, but I prefer that because typically in the laboratory, if you don't heat it, it'll take a week. And if you want the reaction to be done overnight or in a few hours, then you need to heat those reactions. So that's really typical conditions. Man, it is so hard. So you need a strong acid to protonate the carbonyl, and you need an excess of the alcohol to drive the equilibrium towards the ester side of that back and forth equilibrium. Now, one of the most efficient ways to make esters, or one of the most efficient examples of making esters, is cyclic esters. Cyclic esters, if it's a 5 or 6 membered ring, they're super favorable. Boy, they are favorable. Let me go ahead and draw the substrate for this. So if I had to come up with a substrate, what am I seeing here? If I were to just analyze this reaction, well, I can see we're adding an acid catalyst. I can see that water is the byproduct. In this case, I can see it's being heated. You wouldn't even have to heat this because 5-membered rings are so favorable. I can tell this is an esterification, like a Fischer esterification. And I'm making this bond over here as the new bond. We're making this carbon-oxygen bond. It's the new bond. So once you've practiced working problems with this, you'll be able to recognize that this is a Fischer esterification and it's making a ring. So I need to redraw the starting material for this that doesn't have that bond and has the H2O attached to the carbonyl group in some sort of a form. So let me go ahead and draw out that starting material here. The starting material would have these atoms, and you have to practice this in order to be good at it. I can see if I go over here, if you're scared about missing the carbon atoms, then feel free to enumerate them. Okay, I've got a carbonyl group 1, I've got a CH2 group, and notice how I identify that it's a CH2. I don't just say carbon, I say CH2. Over here, I've got a quaternary carbon with no H's, that's carbon 3. And then over here, I have a CH2 group number 4, and it's attached to an oxygen, and I don't break that 4-5 oxygen bond. So let me go ahead and draw the substrate out for this reaction. So the substrate would have a CH2 group number 2. It's attached to a carbon atom number 3 with 2 methyls. There's a CH2 number 4, and it's attached to an oxygen. And so what I really need to do is draw the H2O group that used to be attached. It used to be here. So if this is a Fischer esterification, I must have had an alcohol, and I must have had a carboxylic acid. Let me go ahead and paint this so you can see where, here's the leaving group, that ends up in the water. And then we'll come back over here. Here's the oxygen that ended up forming a new bond. That's the oxygen right there. And you can see that you're going to end up with what a Fischer esterification does is it makes a new bond between the alcohol and the carboxylic acid. You're going to have to practice that. When you make rings, it's super favorable to make 5- and 6-membered rings. There's nothing, you don't need to write the word excess. You can't even write the word excess because these two groups are present in a 1-to-1 stoichiometry. There's no such thing as excess. And you don't need to worry about how fast the reaction is because when you're 5 atoms away, this orange oxygen here collides so frequently, just slams into over and over and over again. That's the advantage of being 5 atoms away, is the number of collisions is so vast and it's so frequent that it's favorable to form 5- and 6-membered rings. So this is a super common type of ester to make as a cyclic ester. And we have a word for cyclic esters. They have a special name. A cyclic ester is referred to as a lactone. Cyclic ester is referred to as a lactone. That's the word we use in organic chemistry for cyclic esters. So lactones and lactonization reactions, a lactonization is making a cyclic ester. Super common because rings in organic chemistry are easier to form than acyclic things. Let's go ahead and look at the mechanism for this reaction, this Fischer esterification. You can't just throw in super powerful nucleophiles because those will be bases that deprotonate the carboxylic acid. So our trick here is we use acids, hydrochloric acid, sometimes sulfuric acid. And I'm symbolizing that over here using this HA, using that HA symbolic acid there. And step 1 is that we're going to stick a proton on the carbonyl group. So let's go ahead and do that. And we're going to end up with this super reactive carbonyl compound. Now, if I put a 3rd bond to that oxygen, I need a positive charge. We would refer to that as an oxonium. 3 bonds to oxygen. The word oxonium doesn't tell you that it's all single bonds. It just tells you 3 bonds of some kind to oxygen. But now it's going to be super easy to attack that carbonyl group. That's really going to be an important focal point for reactivity. So now even a lame nucleophile like an alcohol, like methanol, can easily attack that. So I'm using methanol as my alcohol in this example. Let's go ahead and draw out the arrow pushing for that. So the lone pairs on oxygen can attack, and they can push up the electrons to the O and make that O plus happy. The O doesn't like to have that formal positive charge on there. Don't attack the oxygen. Oh, for gosh sakes. It's got 8 electrons already. It just wants to get rid of the positive charge. It doesn't want more electrons. It wants to get rid of the positive charge instead. Okay, so as we draw out this next intermediate, it's going to get a little crowded in here because I've got all these bonds here. Let me go ahead and draw this nucleophilic oxygen that just attacked. And I'm very clever here because I've written this mechanism enough to know that I need to draw out that OH bond. So now the nucleophile that we just used has a positive charge. It's an oxonium ion, and we need to deprotonate that. From our first step, we had an A- counterion floating around. It's just kind of floating there, waiting for something to do. Well, let's go ahead and draw it here. Look at that. That A- is right there. And so it's so easy for it to pluck that proton off of that oxonium ion. Oxonium ions are very acidic. So let's go ahead and pull that proton off. And when we do that, we end up with this next intermediate here. This is going to be a 6-step mechanism. Kind of like imine formation with 6 steps. It's kind of annoying that there's all these long 6-step mechanisms in this third quarter of organic chemistry. Okay, so when we pull a proton off, now we have HA sitting around here. I'm going to write that HA molecule, our symbolic acid, just kind of floating around. It could reprotonate the methoxy group, but that's boring. That would just take us right back to this previous step if we protonate the methoxy group. So don't do that. We're trying to explain how we go forward to the ester. And so we want to convert one of these 2 hydroxyls, doesn't matter which, into a water leaving group. So we're going to protonate one of them. So let's go ahead and draw, let's go ahead and protonate the one on the bottom. And it's arbitrary because they're indistinguishable. So let's go ahead and draw that protonation event occurring. And so now we have a leaving group attached on here, a water leaving group. I'll put the formal positive charge on there. Here's our methoxy group. And so now we're ready to push out the water molecule. I could use lone pairs on the methoxy or the hydroxy, and I'm going to use the lone pairs on the hydroxy just because that makes the mechanism a little bit simpler. But the lone pairs on both of these oxygen atoms are pushing. The lone pairs on this oxygen are trying to push out the water. The lone pairs on this oxygen are trying to push out the water. And in fact, they're both pushing at the same time. I'm going to use this lone pair here. And I think you have this tendency probably to always do SN2 reactions, but look at this lone pair, it's there all the time, so it's very easy for it to push out this leaving group. And so you end up with, now we can see our carbonyl suddenly appear, our CO pi bond. And this kind of looks like the first intermediate that we had in the very beginning. It looks like a protonated carbonyl, and that's exactly what it is. And so now, just remember the fact that you've got this A- floating around. Let me draw it over here. A- is just floating around. Now I'm going to draw that A- over here, right where we need it. And the last step is we deprotonate that carbonyl, that oxonium ion. We deprotonate that and give the electrons to the oxygen. So super important mechanism here, that's this Fischer esterification. And the importance of these protonated carbonyl intermediates in making this possible. Oh, that bond really is crooked, so let me try to fix that. And there's our ester. It's a 6-step mechanism. And if you wanted the mechanism for hydrolysis of esters using acid, it would be the same intermediates. We would just erase all the red arrows, draw the same intermediates and put different red curved arrows. And we'd have the mechanism going backwards for hydrolysis of esters under acidic conditions. So that's Fischer esterification. really a venerable reaction. All right, we've got this. It's super easy to make amides. I'm going to give you a couple of. I'm going to give you a powerful reagent for making amides that is really a worthwhile reagent. You've got to memorize this reagent. It's called dicyclohexylcarbodiimide. Dicyclohexylcarbodiimide. It's a carbodiimide reagent. Here's the word carbodiimide. The word carbodiimide looks a lot like carbon dioxide. It's like this. There's R groups because nitrogen needs 3 bonds. That's a carbodiimide. And we use this reagent called dicyclohexylcarbodiimide. And I don't expect you to know that reagent. I don't expect you to know the structure, but I do expect you to remember how to abbreviate it in a fashion that every organic chemist knows. We write the words DCC, not PCC. That's an oxidizing agent. DCC. So the recipe here is that you take a carboxylic acid and an amine, and you end up making an amide bond out of that. And the DCC makes that work. So let's take another example. Here's an example of an amine, and built into the same molecule, there's a carboxylic acid. And so you end up generating a new carbon-carbon bond with this reaction. There's the new carbon-carbon bond you generate right there. And so what's the reagent we need? DCC. That's all you need to know. Boy, isn't that easy? It's so easy to make amides. Wow. You don't have to convert the in fact, don't even try. You couldn't convert the carboxylic acid into an acid chloride if there's an amine present. Remember when you make acyl chlorides from carboxylic acid, you can't add pyridine. It ruins the reaction. So you couldn't do this and turn this into a carboxylic acid with thionyl chloride. It wouldn't work. So I'll just write no. You couldn't. So the DCC really is it's simple conceptually. Carboxylic acid plus amine, you add DCC, you get an amide. It's conceptually simple, and it avoids this your need to try to make an activated group out of that carboxylic acid. So down here is the structure of dicyclohexylcarbodiimide, and you can see you're losing the elements of H2 and O out of this reaction. But the H2 and the O end up attached to the carbodiimide. That's what the reagent is for. The carbodiimide reagent itself is used to soak up the 2 H's and the O that disappear from your substrates, end up as a new byproduct it's insoluble as this white powder. You just filter it off and you got pure amide. Boy, what a great reaction. You don't care about how easy it is to purify, but I tell you, in the lab, it's a great reaction. Okay, the last reaction we're going to cover for today is not really practical for organic synthesis, except for making nylon. I'm not quite sure. The problem with this reaction is there's a requirement here that it only works. I'll just state it openly here. It only works if R for R, R prime equals simple alkyl groups. And we don't do reactions like that. We make super complex products. And when you're in the drug industry, you're not doing this with methyl and ethyl and hexyl on there. That's the only time this would work, because the conditions are just incredibly harsh. So in theory, if you take a carboxylic acid and an amide, and you heat them hot enough, you'll get an amide. Or if you take a carboxylic acid and amine and you heat them hot enough, in theory, you could drive off water and give an amide. But most R groups decompose at the temperatures that are required. The initial thing that happens, let me just remind you, the initial thing that happens is an acid-base reaction. You've got a base, that's the amine, you've got a carboxylic acid. So what really happens if you take a carboxylic acid and you don't heat it to 500 degrees is you simply get an acid-base process. And now this is not a nucleophile, and this part is not electrophilic. It's one of the least electrophilic carbonyls. It's so hard to attack, not electrophilic, right? That carbonyl group is not reactive. So when you mix amines and carboxylic acids, nothing good happens. It's only if you heat them at insanely hot temperatures that you can get amides out of them. So I'm going to recommend that you don't ever say that this is a way to synthesize an amide. Don't say you're simply going to heat it. I would never give you an example for making an amide where it would work to simply heat things together. The book says you can do it because they're focusing on the nylon aspect. You can use it to synthesize nylon. But what would I expect you to do? I would expect you to write the DCC. Right? That's so easy. Here's the way to do it. DCC. There you go. It's so easy. Why would you even try to heat this to hundreds of degrees? That doesn't make any sense. There we go. It's that easy to make an amide. Okay, we've learned a bunch of transformations of carboxylic acid derivatives. Forming amides from acyl chlorides, forming esters from acyl chlorides. You could, in theory, you could form an anhydride from an acyl chloride, but we buy our anhydrides. All the acylation reactions you do with acyl chlorides, you can do with anhydrides if you want. We talked about this Fischer esterification. So if you want to make esters just by mixing alcohols and carboxylic acids, you need to use one of the reagents, almost always the alcohol, in an excess and drive the equilibrium. And you need that acid is in there to protonate the carbonyl so that even an alcohol OH can act as a nucleophile if you protonate the carbonyl. You should remember that from the last chapter, or maybe we're reinforcing that from the last chapter. All right, I will keep on working. We've got so many distractions with the elections and all this other stuff, and I just need to ask you to try to stay focused. Keep your attention on practicing these tools so that you can answer the questions on our exam. I'm going to ask you about reactions you've never seen before, so you need to practice these tools until you're good enough to draw mechanisms and products and reagents for reactions you've never seen before. So keep it up, great work, and I will see you guys on Friday.